Heat trace. In this presentation, we're going to be looking at different uses for heat trace, a basic concept of operation, and a few different types of control. Heat trace is an insulated cable that generates consistent heat levels along its entire length when energized. Its primary use is to maintain constant temperature of an object and prevent freezing. We can see an example of heat trace below, as well as an example of its installation on a piping system. In the industrial sector, it's used to prevent liquids from becoming too thick or freezing due to heat loss. Often, it has very specialized arrangements for the wrapping around different objects like valves or supports to try to reduce the heat loss, and then additional insulation connected around to try to keep the heat internal. It can also be used on roofs to melt snow above eaves troughs and downpipes. It can be used in roadways and walkways to melt snow on ramps to underground garages or outdoor stairways. And everywhere it can be used to prevent frozen water pipes. The basics of heat trace are that when we apply a voltage, the wires heat up, but they don't heat up to such a point that the insulation is damaged. They heat up to the point that they're rated for. And the heat that they generate is constant throughout their entire length. There's a few different types of heat trace that exist in industry: series, parallel, and self-regulating, not to mention a bit of an outlier called skin effect heating. Fixed resistance heat trace: a voltage is applied and heat is generated. It's a single wire. And because it's a single wire, it comes in many different forms. It can be two wires inside one stainless steel sheath, or it can be a single wire that is continuous all the way throughout its length. This is a series fixed resistance heat trace. And as you can see at the end, those two wires must be connected together with a termination. Another option would be to have two exposed ends, and those two ends would then be connected to the power source. There's a number of different ways that it can be utilized. Parallel fixed resistance heat trace is slightly different. Parallel fixed heat trace, when voltage is applied, heat is generated. However, there's always two conductors, and the parallel connection of them means that the current rating is slightly different. We also have three-phase, not just single phase. And with three-phase heat trace, the end of this cable, if it were down here somewhere, would have all three of those wires terminated together, creating a Y or star point. Self-regulating variable resistance heat trace is by far one of the most common. And that's because there's a semiconductor that connects the two power conductors together. And that semiconductor then varies with heat. The important thing about self-regulating heat trace is that the current and the heat will depend on the temperature of the object. If there's a cold pipe that it is wrapped to, there will then be more conductive paths due to the semiconductor material. This will then cause more current to flow and more heat will be generated. If, however, this cable were wrapped onto a hot pipe, there will be less conductive paths due to the semiconductor connection. Less current will flow and less heat will then be produced. So this would be heat trace on a cold pipe. And as you can see, a significant amount of current flows, which means a lot of watts of heat are being generated. Whereas on this system, we have it wrapped onto a hot pipe, only a very small amount of current will flow and a very small amount of heat is generated. In this way, it's self-regulating. It will keep the temperature of a pipe constant without the need for additional controls. Here's an example or a picture of what it looks like. And you can see here that it has a rating of voltage as well as how many watts per foot it would consume and generate heat from. Skin effect heat tracing is very different and very much an industrial application. It is a single conductor which is connected or bonded rather to the actual process piping itself. It uses the understanding of skin effect in AC so that there is no shock hazard. The reason there's zero potential shock hazard is because the return conductor is actually the conduit that the wire is installed in. And because of that, the current that's returning to the AC source will only flow on the interior surface of that metal pipe. Now, as the current flows, and we can see here current in the insulated conductor and current on the interior surface of the pipe, it will generate heat simply by electrons flowing over the metal. That heat, due to the pipe being welded to the product pipeline, will then transfer through conduction. Now here's an example at a job site. Controlling heat trace. These are very basic forms of control and ones that we see in many different areas. Line voltage thermostat, contactor controlled, or electronic controlled. Line voltage thermostat will simply turn on or off the heat trace based on the temperature around the thermostat. Contactor controlled does the same thing, however, the thermostat only controls the contactor. This would be used in a situation where the current value of the heat trace cable to be controlled exceeds the rating of the thermostat. And finally, electronic controllers, where we can use electronics to accurately control how hot the heat trace gets based on feedback from a sensor. This is an example of a electronic heat trace controller. And another type. Wrapping arrangements are very specific, and although it states down there that heat trace is never wrapped over top of itself, what it should say is that heat trace is applied to different objects based on the manufacturer's recommendations.